This is 8.7. And this is on. Polar equations and graphs. So in algebra, you do a lot of shit with the Cartesian coordinate system. Cartesian or rectangular coordinate system. And we've used it in here. It's the XY. And we call it rectangular because it makes a fucking grid when you like use graph paper to graph just about anything. I got an example that I know I'm using a little bit. Polar. Let's do that version here, like y equals 2x minus 4. This is algebra, you go down 4, minus 4 tells you to go down 4. The 2 is the slope. 2 over 1 is m, so rise over run. Up 2 over 1, up 2 over 1, 2 over 1, and you can make a line. It's called the Cartesian coordinate system because these effectively, if you if you're doing it on grid paper, these we have like vertical lines and it makes rectangles. You do like graph paper. This is not the only coordinate system. Trigonometry does a lot of stuff with r and theta. So polar coordinates. The polar coordinate system uses r theta. I think the easiest way to view this is go a distance to the along the x-axis r. So like negative r would be to the left. And then rotate counterclockwise theta. Other versions of this. You can do the same, you're always gonna have to rotate the counterclockwise theta. But another version is to go the positive distance r. Rotate. And then if r is negative, flip it. Point in the opposite direction 180 degrees. So what this is based on is. Where they come up with this name. The origin is like the pole. They call it the pole. And we have some ray that's out a distance of a length r. And this is called a ray, but it's also the name for it is the polar axis. And this thing rotates. Rotates where you get it where you want. The polar axis is generally called the x-axis version, and the ray rotates away from it. So the polar axis is almost uniformly the x-axis. And the ray rotates counterclockwise from it. Now, if I go out a distance r, I'm gonna use this eraser as my ray. And I rotate, I keep rotating. What kind of shape does the tip of the eraser make? Makes a circle. So we don't use rectangles on our graph, we use circles. A polar graph often looks like this. It has concentric rings that measure how far out a radius is. So like that's the third ring, this would be r equals 3. And in an effort to not overdo it, they always show the rings. And they're evenly spaced. They need to be the same distance apart. And just like graph paper has some guiding lines so that you can follow it easier. Polar graphs, if you have polar graph paper, it has guiding lines. They tend to do it at the 30 and 60 degree marks. So they'll go like 30 degrees and they'll have a line like this that extends both ways. They'll do it at 60, every 30 degrees shows up. So that when you're trying to sketch something, you can sketch it kind of quick. Very much looks like a spider web. So in polar coordinates, let's map a couple points. Let's map where 135 degrees is. What you're gonna do is you're gonna go out a distance 4 from the center. And rotate 135 degrees. What angle would that put us at in quadrant 2? Well, yeah, but I guess I said that poorly. It's like the 45 mark, when you're going between the 90 and the 180. It's a handy way of thinking about it, but when it is definitely 135. So that's the point P. It's on the fourth ring at 135 degrees. What about Q, -3 pi/6? There's 2 ways to get this. One of them is go -3 from the center. Go left 3. Rotate counterclockwise, which is this way, pi/6. Pi/6 is how many degrees? 30. Wait, 1, 2, 3, puts us right here. That's where Q is. That's -3, 30 degrees. The other way of doing this is go to positive version, 1, 2, 3. Rotate so it hits here. And then flip it. And when you flip it, it points in the exact opposite direction, the same distance. So however you want to do it is up to you.
Wait, why? Are you supposed to rotate them counterclockwise, right? So why is P on that side?
Because we rotated 135 degrees from the x-axis.
Oh, okay, I was getting confused with that. Okay,
And for Q, it goes -3. So it's going in this direction and it rotates pi/6, which is 30 degrees. It ends up on that line.
Okay.
Does that make sense? Are you guys tracking that? Are you picking up what I'm putting down? I like that phrase. You can also go the positive version and then flip the arrow and point it in the opposite direction. Some people like doing it that way, either way works. Where would two, we'll call this point R, 2 negative pi/2 be?
Go out 2 and then rotate clockwise pi/2.
We're gonna rotate clockwise pi/2 because it's going in the opposite direction of the normal rotation. So we go out to, how far is pi/2 in degrees?
60. Oh, 90, never mind.
You gotta go back to that fucking
9.
drawing
I
chart there,
told
buddy.
you, dude.
He just got done telling me how he like was embarrassed. Of his answers in the previous class, this is right before class started. And then he went and fucking practiced up on his fucking shit, and I hit him with pi/2, one of the fucking easiest ones to do. And he comes up with 60 goddamn degrees.
Hey, man,
so if
I'm gonna get a good grade on that test, that's all I know.
so if it's positive, it's gonna be counterclockwise, and if it's negative, it's gonna be,
It rotates the other direction.
okay.
So this angle is always matching up with what we did with our unit circle. Right? Pi/2, like pi/3 would be clockwise or counterclockwise. When we did negative degrees, we went backwards, we went clockwise. So this is still the same activity you do on the unit circle, now we're just treating it. Any point on it is the tip of a vector. And it changes the grid circle to something like this, and you may be like, well, why the fuck are we doing that? Well, wait till we see polar equations. Interestingly enough. And this part I actually might put on your test, because this isn't like the hard shit. Every point can be written 3 ways. Or 4 ways. Well, an infinite number of ways, but we're gonna go with 4 ways. Let's use that P for 135. So for 135 degrees is one way to do it. I could rotate -45 degrees. Which would put me there and use -4. I could do -4, -45 degrees. Because -45 would put me here, and then this makes this vector, and I do the opposite when I use it. I could sweep out all the way around, add another 180 to it. 180 to this would put us at 315 degrees. And I could do -4. Or I could rotate clockwise, I'd have to go around 180 to 225. I could go -225 degrees. And then I'm right on that line, and I just go distance 4. So 2 of them have R less than 0. 2 of them have R greater than 0. And then you could also add 360N to any of those. And get the same thing. But those are the four base ones where you're still within the same region. So what if we are given our points in Cartesian and we wanna use polar? This is usually what happens. You're not given shit in polar, you're given shit in Cartesian. And the mathematics looks very ugly in rectangular form. Just picture our equations. X equals r cosine theta. We've used this the entire class. Y equals r sine theta. R is the square root of x squared plus y squared. And theta equals tangent inverse of y over x. It's usually this MFer floating around in your problem. That makes the math suck. But being able to write it as a single variable r is actually pretty useful. And it turns out when you're doing calculus, all of the operations work the same way, whether you're working in x or r. X and y or r and theta. There's just a little shift you have to do when you change systems. So sometimes if things are round. Doing stuff in polar coordinates is much more useful. If you're going to take calculus. You will use polar coordinates a lot. Maybe not in Calc 1, but Calc 2 and Calc 3 are abundant with them. Many things in life that we do are round. Like. The globe is round, it's spherical, well, close to spherical, it's an oblate. But we treat the atomic structure as a sphere. Wheels are round, a lot of things that we do fucking mathematics and engineering on have circular shapes. Or spherical shapes, so being able to do stuff in easier math in those systems is desirable. That's why I came up with all this shit. So let's say we had the point, this is in Cartesian. 6 negative 6 root 3. Okay. Rewrite this in polar. This is actually not the shitty part there. This part is fairly easy. It latches up with the unit circle. This isn't much beyond what you did in chapter 5 and 6. And what we did a couple sections ago, switching between polar and this. We're just now graphing in that format. How do I get R?
Plug into the equation, so it'd be square root of 6 squared plus negative 6 square root 3 squared. That's 36 plus 36 times 30.
I'm actually gonna leave it like that. Work smarter, not harder. 36 plus 36 times 3. If I factor out the 36, you don't need a calculator to do this. I have a 1 plus a 3. I have square root of 36 and square root of 4. Both of those you should hopefully know the answer to. Square root of 36 is square root of 4, 2, so it's 12. And then I didn't need to figure out what 36 times 3 is. And it was already in a factored form, we didn't need to fucking make it harder. Just. What about tangent theta? Or what's theta?
Negative 6 root 3 over 6. Tangent inverse of that.
So we have tangent inverse of negative root three. That is one, what's the positive reference angle of that? We'll deal with the negative later.
Is it 60 degrees? You're talking about the root three?
Yeah, the root three,
The tan root three is 60 degrees, right?
yes. So the reference angle would be 60 degrees, but we're going negative. So it should be negative 60. And tangent inverse runs from 90 to 1 or negative 90 or to 90, so that's a valid range. Negative 60 is in that region. Apparently 6 root, it seems kind of weird, I don't know what 6 times square root of 3 is, maybe like 9-ish. I don't know. What is square root of 3 is 1.7, 6 times it's gotta be about 9, maybe 10. 10.4. So like if I approximated that 6 and negative 10.4. We're going left 6 down negative 10.4. More downward than left. Like in Cartesian, we're doing this. But in polar,
Let's get your paper up.
yeah, in
Thank you.
polar. We're rotating negative 60 degrees and going out 12. That's a length of 12 and negative 60 degrees. Granted, most of the time, if you already have it in X and Y, sketching in X and Y is easier. But that's not always true, cup 3. When you're doing stuff in 3 dimensions, recognizing something's a circle or a sphere. Is actually easier to picture when you're drawing a 3D plane and how to like map it out. Rather than going, where are the X, Y, Z fucking coordinates, you're like, it's hard. But like making a cone, like a snow cone with the circles, just keeps getting bigger the higher up you go. Snow cone. Like. Drawing a circle is kind of like sketching the circle from an angle. We've all seen them, you've seen a snow cone, I hope, has anyone never had a snow cone? I make a lot of assumptions about shit. Okay, good.
Oh, so it's hot as fuck here.
If you haven't had a snow cone, you either fucking didn't grow up here and grew up rich. Like one of the. Both of those have to have been meant to not have snow cone. Because it's cheap, it's easy to make. It's definitely for low income, middle income people. And hot is always a good factor, you don't wanna eat this shit fucking Alaska.
Nah. You know you're broke if you had to use the blender, you just blended some fucking ice and threw some flavoring in that bitch. Oh yeah,
A little bit Kool-Aid,
hell yeah.
don't want to like make the Kool-Aid not like, don't use the normal amount of water, just like put a little bit of water in it, so it's like thicker.
It's very potent.
Potent snow cone.
Hey, can you show me how you got equals 12, the R equals 12? That square root 4, I'm kind of trouble seeing.
Did you go from here to here? See what I did there?
No, I don't know how you did that.
So I have effectively 36 times 1 and 36 times 3. I did the reverse of factoring or distributing. If I had 36 times 1 plus 3 and I distributed. Kind of like we would do if we had X plus Y, you would have to distribute. I can do that here. And have 36 times 1 plus 36 times 3. Like if I had X plus 3Y. If I had variables with it, you would have to distribute. Get 36x plus, and the math I was trying to avoid was 36 times 3. But if the thing shows up twice, you can pull it out, and if it's the whole number itself, you leave behind a 1. And then you're adding together. This is an algebra thing, it's not something.
Oh, I see the 1 plus 3 is 4, okay, yeah, that's fancy.
It's a handy algebra thing. Like makes you so you can do math quicker without having to fucking rely on a calculator all the time. Calculators will slow you down if you finally learn how to do basic math. This is basic math, it's the algebra.
Why go the factoring route when you could just look at it as 36 plus 36 plus 36 plus 36?
That's another excellent way of doing it. If that works better for you, and apparently Spencer liked that. Spencer is saying, don't do this as that, right? We had a 36. And then 36 times 3 is 36 plus 36 plus 36. And there we can see we have 436s. That's recognizing that multiplication is repeated addition. Not everybody's comfortable doing that, but that's really what multiplication is, repeated addition. 2 times 3. Is either 3 plus 3, you do that 2 times, or you're doing plus 2 3 times. Like, there's 2 ways to write, it's repeated multiplication or repeated addition. Multiple ways to get that done. You can also go to the calculator. Thing with the calculator though, this is easy to fuck up in the calculator. And the further you go in mathematics, the more shit you have to put in the calculator all at once, and the easier it is to fuck up. Cause if you don't fucking have a parentheses there, they happened to calculate just today. They gave me the wrong answer, I'm like, that doesn't sound right. I didn't know what the answer was, but it did sound right, just like eyeballing it didn't sound right. Dave was like, this shit is deep.
Yeah,
It's right
these are
up-
like those skills you whip them out with.
It's quicker than grabbing a calculator when you know how to do it, right?
Yeah. Yeah, the calculator sometimes, like you say,
Or having you gotta take your time keying it in, right, cause you can fuck that up. And then you're like, you always get an answer that you don't, unless it's a fucking whole number like 12. You always get an answer that you don't fucking like. Cause it's got some fucking unending decimal number, so you throw it in and you gotta do it twice, and then just make sure you get the same fucking number. So most people are doing it twice, and then if they didn't fucking match. Ah, fuck, which was one of the ways I miskeyed, now I gotta do it a third fucking time. I don't know, that's how I am, cause I never like the answers. I almost always, if the problem had a bunch of fucking steps in the calculator, I do it a couple times. I've learned it takes fucking way longer to do the calculator. And feel confident in the answer just than doing some basic arithmetic. Manipulation of numbers. Alright. Next page. We graphed. Y equals 2x minus 4 a little bit ago. What is this in the R data system? Polar system. This is easy to overthink. What does y equal in polar coordinates?
The data.
There's data in it.
Ours, no,
Is it the
you
tangent?
just told us,
So we just had it.
yeah, we
Pre-
just had it.
What?
Say,
No,
is it R sin theta?
it's R sin data. We've used the y equals R sin theta multiple times in this class. In fact. The first time you saw this was this version. Sin theta equals y over r. Opposite over adjacent, or opposite over hypotenuse. You've seen this formula, and that's x. That's how you get cosine is, x is r cosine theta. So we're gonna have r sin theta equals 2 times, the x version is r cosine theta. Minus 4. Now, usually they like one letter solve for the other. So I could subtract 2r cosine theta from both sides. You're not gonna like this. But there's a lesson here. We get r minus 2r cosine theta equals -4. If we factor out the r, what happens? David. Just asked this question, but it didn't have r and cosine theta in it. This is the very process we just talked about. If I factor out an R, what's left in the first term?
Should that one there, the R minus two R, should that be R sine theta?
Yes, it should. Should be R sine theta minus two R cosine theta, my bad.
So I guess sine minus two cosine.
Yes. That was the hesitation, you're like, I don't even know where you got the fucking, where'd the sign go, I get
The
it.
factory, fuck's me up.
Oh, you did the factory, fine, this is your fucking moron teacher fucking. Wrote R rather than R sine theta, you couldn't even fucking copy the previous line down. You see how easy it is to fake and make that mistake? Now, you guys do the same shit on tests, but you'll leave out equal signs and you'll like. Especially if you don't leave, if you leave out the equal sign or like don't write the left, what you're doing every time along the way. It's really easy to lose track of it, try to be consistent along the whole way. Now, if I want R by myself, I gotta divide both sides by that shitty fucking value. So R equals -4 over sine theta minus 2 cosine theta. Or if I move the negative to the bottom, I can make it this positive and do 2 cosine theta minus sine theta. So that's my R. Or we could graph y equals 2x minus 4. Which one of these sounds like they're easier to graph?
2x minus 4.
Y equals 2x minus 4. So sometimes rectangular system is the way to fucking go. Don't change the polar if it's not good in polar. A straight line is great with straight line system. What about x squared plus y squared equals 25? What is that in polar? Oh. The same type of process, you don't have to do it in your head. What do we replace x with?
R cosine theta, right?
So we got r cosine theta squared, and what do we replace y with?
R sine theta.
So if you distribute, you got r squared times cosine squared theta plus sine squared theta.
Oh. 1.
That's 1. We get r squared equals 25, so what does r equal? 5. There was a quicker way to get there. You just were drawing blanks, so I went with the one that you were most likely to remember. We could have started with this. And just squared both sides here. You get r squared equals x squared plus y squared. And you plug that bitch in. Either way, you get r squared equals 25, so r equals 5. Guess how easy that is to draw? Start with this center. You go out 5. And you just go. There was no theta mentioned, so it's all thetas. Every angle works. Theta is not part of the equation, so all work. You have seen that idea where if the thing is not present, it's any value. If I were to have said, let's graph x equals 2. The graph of x equals 2 is just go over 2. And since y wasn't given, it's any y value where x equals 2. Y wasn't given, so we use all y's. Theta is not given, we use all thetas. It's not very often you get a problem where in polar you get a theta but no r. Is there one that has it? Yeah, let's do that. Just add this bitch in right now. How about y equals x?
Fine.
This one's easy in both systems. Y equals x is easy in both systems. It's a diagonal line. Let's show that we get, this is theta equals 45 degrees and r is irrelevant. Let's show that we get theta equals 45 or pi over 4 by plugging in and doing the math. In fact, this leads to the idea of solving a polar equation. If I plug in what we got r sine theta equals r cosine theta. You really don't want to divide by r. You wanna move one over by subtracting it. We're gonna do some practice your algebra here. Factor out the r. And now we've got effectively a times b equals 0. It's called the zero product property in algebra. Either a equals 0, r equals 0, or sine theta minus cosine theta equals 0. Which is kind of what we would have got if we divided by r, but we lose the r equals 0, that's why you should do it. Well, this one, I'll move the theta back over, cosine theta back over, I'll add it to both sides. I divide both sides by cosine theta. You get tangent theta equals 1. And what angle does tangent theta equal 1 at? 45 degrees from pi over 4. So we can get a line with no r, where there's no r in this equation. This is just doing theta equals tangent inverse of 1. There is no r present. This r equals 0 is already on the line, r equals 0 is right there. So we don't even need it to use it to describe it in polar. This is sufficient in polar. But most of the time, a straight line in polar is easier just in the XY system. But you can generate it, but sometimes going to polar sucks. As we saw in the last one, I wouldn't even know how to fucking go about. You know how you have to go about doing this one? And if you look around, you know how you have to go about grabbing this? You can't use fucking basic, like, oh, I know what this looks like. You literally gotta plug in thetas. Which sounds like a pain in the ass. And it is a pain in the ass, and you're about to find out.
So you just test points essentially?
You test a lot of, you wanna do a lot of points to see what it looks like. This took, I was already like putting her head down, she's like, this shit sucks already, I don't even like it, fuck it, I'm out. I'll wait till everyone looks like they're done writing this before I continue. Oh, you guys got so lucky. So lucky, my wife made beans and ham. The other day, and I had it yesterday for lunch, she's like, this is what we're having for lunch. And I'm like, oh, those poor sons of bitches and tricks, but it's right about the time we get around to that time tomorrow. But nope, I was just literally been like all day and like I get here and it's gone, gas is gone. You guys got lucky. I almost took a picture. Of the bowl of beans and just like laid it out on the camera up here. And said, my wife hates you, this is what I had for lunch recently. This is a recent meal, guess, you know, what happens, what happens. Alright, so these are a bunch of polar equations. If you have A where like A is cosine theta or 2 cosine theta or 3 cosine theta, it's really just saying how big the circle is. You're making a circle that like when r equals a cosine theta, it's a circle that's off key, off center, it's along the x-axis, it's recentered. If you do a sine theta, it's centered up here. If you have a double angle, it makes something called the lemniscate. So cosine is along the x-axis, sine 2 theta does a diagonal. When you have a whole, like when this number is not 2, but it's some other number, you get this shit down here. Notice the only difference between, oh, that has an a square. We don't even, why does there need to be an a squared up there? Oh, just make it clear that it's a distance a. And these things are the same things as this, where we don't have a 2, we're using a different number than 2. We're gonna graph some of these by hand. Cause you're not gonna recognize what they are. This is like usually, more often than not, this is what you need to do if you don't have. Computer or your phone near you. Does anyone want to take a picture of this?
Yes.
Like I'll scan it, add to the notes.
The last page of the chapter too.
David's a go-getter, he likes print shit out. The last page of the chapter,
I printed out and I never.
chapter or section?
Yeah, page 847, 8.7, chapter.
Oh, so yeah, 8.7, we're doing 8.8 on Tuesday. We do have one more section. Let's take a look at getting some of that. I'm going to put that in here to scan, so it's part of the lecture notes. Then I gotta remember to take it back out. We are going to graph. Let's take a 10-minute break. This is gonna take a little while, you know, it's already 3:55. But what we're gonna do is graph r equals 1 minus sine theta when we get back. It's pretty bright. Turn on the brightness. Alright, so how the fuck are we gonna draw this? Well. I'm gonna make a giant table of theta. And it's generally a good idea to do like maybe every 30 degrees, sometimes that's not enough, as you'll see in the next problem. I'm gonna 0, 30, 60. 90. 120, 150, 180. This is gonna be Patrick's fucking. This is Patrick's wet dream coming
I'm
up here.
fucking,
He gets to practice his skills.
crickets, that's what you're gonna hear right now.
Then I'm gonna make a column for sine theta. And maybe like we'll do a decimal column for sine theta. Cause it's easier to do sine theta with the angles we use just off the unit circle. But then we'll do r. We're gonna take the previous column, do 1 minus sine theta, which is like 1 minus the decimal we had in the previous column. This is what you did when you first learned to graph in algebra. They didn't show you like slope and rise over run, shit like that, they just said start plotting points, plugging in an x, see what y you get, and make a bunch of points and then connect the dots. That's what this is, it's a game of connect the fucking dots. That game you learn to do when you're fucking 5 years old, they're training you to fucking be a mathematician. And maybe to make this a little bit easier to see, maybe every 2 sets of degrees, I'll put a little line so that I can keep track of. The rows better, I don't want a grid line for every fucking thing. But I'll do that, a little easier to follow. You'll find if you don't do this like horizontal line every 2 or 3. You just have a fucking giant table, your shit will get a little out of alignment, and then you're like, which one is this going with, and it's fucking hard to read. These are Jedi pro tips. What is sine of 0? Oh my god,
0.
you are,
I'm just seeing
Your
how I'm
failure
rage
is
baiting you at this
complete.
point.
you gotta be fucking trolling me at this point. Sine of 0 is not 1,
Nope.
cosine of 0 is 1, what is sine of 0? 0.
I was rage baiting you, by the way. I promise. I just literally looked at the unit circle to double check, so I was like, no fucking way, I'm gonna fuck this shit up again, dude. Yeah, promise, pinky promise.
Sine of 30.
Wow.
Sine of 60.
We're in 2.
You're done, alright, so let's do this for our fucking Jedi Knight here. 30 degrees. 45.
Oh, I did 45, that's why, my
I'll
bad.
put 60 here and 45 is in the middle.
My brain was thinking the unit circle, and I just skipped to the next one. I didn't actually pay attention to the.
So. They go for sine, it's square root of 0 over 4. Square root of 1 over 4. Square root of 2 over 4. Square root of 3 over 4. Square root of 4 over 4. The square, like, it follows a pattern. But the square root of 4 on bottom is always 2, so like this is effectively 0 over 2 for that one, which is 0. Square root of 1/4 is 1/2. Square root of 2 doesn't change, but the bottom is 2. Square root of 3 doesn't change, but the bottom is 2. And 4 over 4 is 1, so the square root of 4 is 1. So it follows a pattern. The numerator is 0, square root of 1, square root of 2, square root of 3, square root of 4. So maybe you'll quit, that's what it is, you always put the 60 degrees as 45.
Yeah, that's literally, I just skip it in my head, and then I'm like, oh shit, wait,
That's not the mistakes he was making on the test either.
it was not.
But that's what he's been doing in class consistently for like last 3 classes, it's fucking great. Alright. Root 3 over 2. And that's 1. What's 120 degrees? $150. 180. Notice the pattern rises and then falls. It's a symmetrical sequence there. 210 is what? Now we're dipping into the negatives. So it's gonna follow the same pattern we did above, but now it's gonna have negatives. Negative 1/2, negative root 3 over 2, negative 1. Negative root 3 over 2, negative 1/2, and back to 0. It's a sequence. The only one that's really a challenge on here is what is square root of 3 over 2? This is like 1/2 is 0.5. So as soon as we find out what square root of 3 over 2 is, we can fill in all the other rows. And we 0.8, we're gonna go with 0.87. And we have negative 0.87. So now we're gonna do 1 minus the previous column. 1 minus 0 is 1. 1 minus 0.5 is 0.5. And I'm gonna stop writing the minus part and just show the calculations. Now we go up to 1 minus, I'll show that 1 minus a negative 0.5. Turns into a plus. So the values start being bigger than 1.
And there are the beans.
Residuals. Aftermath, afterquake,
Aftershock.
aftershock, there we go. Make sure everyone has a chance to write this down. We're almost there, we have the table done, it's not just plotting and recognizing what we need to plot.
Wouldn't 90 be 0? Cause isn't it 1 minus sine of theta? Sine of theta is 1.
What happens when you start going too fast? Get all cocky. Like that shit. Seems like Patrick are like a fucking godsend to teachers. Cause a lot of times students, after they make their fucking first mistake verbally. They're like, they fucking get embarrassed, they clam up, they stop answering questions. That fucking sucks. Having students, at least 1 or 2 students participate, can help move the equation or the class forward, help getting people think. Teachers not just throwing the information at you. And. When someone's consistent with the number of mistakes Patrick does, and just fucking continually makes. And he still gives answers, it's like, maybe if he does, it's not so bad. There's nothing wrong with it, yeah, the teacher's making fun of him, but it's a good fun. I do the same, you just watch me do the same fuck ups, I fuck up all the time,
Hey, I got an A in the class, man, so I'll keep fucking up.
right?
I think you said at the beginning of the class, the masters failed more times than.
They succeed,
Then
then
the
students
students try.
even try, yeah. I have gotten more problems wrong than you guys have even fucking tried.
That's what it is, it's.
The more classes you take, that starts trickling away, but. Yeah,
Gotta take the shot, you know?
okay, yeah. You don't take the shot. You have no way of winning. What is it, you miss 100% of the shots you don't take, what is that, Gretzky? Wayne Gretzky, I think it's a hockey quote,
Yeah.
I'm not a hockey person, but I think
Michael
it's.
Scott.
What?
Michael Scott.
It's a Michael Scott quote.
There's no way Michael Scott said that correctly.
He took the quote and then put Gretzky and then he put himself.
Oh, okay,
Put all
okay,
that
yeah.
under him.
Michael Mike's. They have a show, I don't know if it got canceled or not. It takes place in a hospital that does the same shit. As The Office does. Where they treat it as like a mockumentary. And it was pretty funny, like managing a hospital. And like, oh, we're so excited to get like this new machine that no hospital in vicinity has, oh wait, look at the fucking bill on this, nope, send it back. Something like that. Employee of the month, the manager did not wanna pick the employee of the month. asked someone else, so the employee was the previous employee of the month. He gave a reason why every other fucking person would not make a good employee of the month. And yeah, it was a funny shit, it was. I don't know, I'll look it up later on. It's the last, it was in the last year, it was recent. So it just might be on their hiatus till the next season. Alright, so. This was our R column, this is our theta column. So if we go and write them as R theta, we can get our coordinate system. This is 1 and 0 degrees. This is 0.5 and 30 degrees. 0.13 and 60 degrees. 0 and 90 degrees. And if you organize your table well, you actually will have them side by side, but I didn't do that because I never remembered to put a column for R in the beginning. But it's not that bad. Now what I'm gonna do. What is my biggest radius here? 2. I really only need to go out 2 rings. But if I make each ring 1, it's gonna be a pain in the ass to do like 0.13 or 0.87. So what I recommend doing is maybe like making more rings and where not every single ring is 1 step. So if I do like. Every 0.25. That's gonna make this ring here 1. Maybe I'll do this one in red. I'm doing every ring is 0.25. Cause it's gonna be easier to plot the 0.13, 0.87 if I can. Like, it's about, each of those numbers is about halfway between 2 circles. And I need to do this out to 2, so I need some more lines. I need to go out another 4. You could have got away with doing this with 2 circles or 3 circles. But I'm gonna do a pretty good job of plotting the points with 4 circles. Cause 0.13 is like close to halfway between 0 and 0.25. And 0.87 is about halfway between 0.75 and 1. So I can like fucking plot halfway points between rings pretty easy. And this outer one is my R equals 2 circle. And since I have the 30 degrees, I was doing increments of 30 degrees. I'm just gonna lightly make like a 30-degree tracer lines. So I can get an idea of where I'm fucking aiming at. Just a light fucking sketch. I should have done the black lines fairly light too. Just giving me an idea, like those are the thetas that I'm gonna be landing on. So having an idea where they are makes it gonna, so doing the later things is easy. Then you just go through, you just gotta plot each fucking point one at a time. 1, 0 goes outer radius 1 and no degrees, it drops the value there. So this is our first point up here, 1, 0, I got that right here. And then if I go out only 2 circles, 0.5, I go 30 degrees, I've got a point right here. So that's my 30-degree mark is my dot there. My 60-degree mark has gotta be really close to 0, about halfway between 0 and 0.25. That's my 60-degree. And then I've got 0, no radius at the 90-degree mark, I'm back at the center. So if I were to draw what's happened so far, it's doing something like this. We're gonna connect the dots, but make them like curvy. Don't just do them one at a time and connect them like it looks like a fucking constellation. We want curves in there. Then I'm gonna keep going, I've got 0.13 and 120 degrees is right along there. At the 150, I'm out 2 rings right there. Oh. Nope, right there. And when I'm at 180 degrees, I'm out 1. Right there. So it looks like it's doing that. It's got 2 little hills. I keep going. At 210 degrees, I gotta go out 1.5. So that's 1, 1.25, 1.5 is right there. Did I not draw enough fucking rings? I didn't draw enough fucking rings. Look at this sumbitch. I didn't go out 4. That's the R equals 2 line. When I go 240 degrees, it's this line right here, 1.87 is almost all the way out to the edge. And when we're at 270 straight down, we are at the 2 units. So this is doing this. So far, we got something that looks like this. Well, I made that a little more extreme than I need to, like that. And now I go along with 300 degrees, that's this line, that's 1.87. I do the 330, we're at 1.5. And when I get to 360, that should say 1, I did subtracting back there. So it's doing this. And if I do it without the graph lines over there, I got something like this. What shape does that look like?
Heart.
Looks like a heart, right? They call this a cardioid. A cardiologist does what?
Heart health.
Heart health. Same thing, that's where it's, I assume Latin. We call it cardiology. But without drawing it, you may not recognize it, there's just, so we get different shapes. When you have theta and it's just theta in here, doing every 30 degrees is usually pretty good. Every 45, not so much, you like it good, you don't, maybe you lose a little bit of curvature, you're not quite sure what you're doing. Every 30 degrees kind of helps. Guys ready to see another one? I'm gonna show the idea of the next one, this is way fucking worse to draw. Cause you gotta, how many you gotta do? We'll start it, show you how to make the table. And then go on to a more fun one, called the Archimedes. So on this one, we're gonna graph R equals 4 cosine 3 theta. So here I'm gonna get smart, I'm gonna make a column for R first, then theta. And if your base is, if this is like n theta inside. Go through and do all like the 30, 60, 90, that shit. Divide that by n, those are the steps you wanna take. If we do every 30, 60, 90 on theta now, we like don't have enough points. So R theta, R 3 theta, cause that's what's in the equation. And then we'll figure out what cosine of 3 theta is. And we'll do 4 times that. So what we're gonna do is, since it was 3 theta, I'm gonna divide all of my degrees by 3. And see what kind of pattern forms. If you can't recognize it after 3, you're not very good at patterns. What's 30 divided by 3? What is 60 divided by 3? What is 90 divided by 3? 30. What's the pattern? Every 10 degrees. So. You're really not gonna see even enough unless you do the full 360. But it's kind of handy to see what 3 theta is doing. 3 theta would be 0, 30, 60, 90, 120. I need my tracer lines in here now. $150, $180, $210, $240, $270. When theta gets up to 120. These values are gonna start to repeat. Because we hit the 360 mark on 3 theta. Since we're gonna do cosine of 3 theta, that's what really matters. So whatever sequence we get here. These values for this. Are going to repeat every 120 degrees. And the easiest way to see that is go, what's the full circle? The full circle is 360. I'm gonna do that divided by 3 and I get 120. So that you can see where the stopping point is right there. All right, here's your redemption arc.
No.
No, I just got done saying you don't give up. Don't do this to me.
Where we starting?
You fucked up 0 degrees last time, so why don't we start there?
Cosine of 0 degrees.
Cosine of 0 degrees, 1. What's cosine of 30?
Square root of 3 over 2.
Yes. 60?
1/2. I almost said fucking square root of 2 over 2. Fuck man.
And cosine of 90 is 0. Cosine of 120? Cosine of 150? -√3/2, excellent. 180 is cosine of 180?
No, stop though. I'm thinking before I say shit, I'm about to think.
He's already throwing hand just gang signs over here. He's doing this. What do you think sign is he showing right there? You're about to throw up a 0. I know you wanna say 0, it's not 0,
-1.
-1.
See, it's just.
Abby's to
give me
your
a second.
rescue. What about 210?
-√3.
Yes. This thing is going to reverse the sequence that we just had up here. So this should go -1/2. This should go 0. This should go 1/2. This should go √3/2, and that should be 1 again. The sine one didn't work like that. It didn't reverse sequence, it kind of like repeated with negatives. We already did the calculator work on what some of this shit was. I'm gonna write this as 4 times 1. 4 times 0.87. 4 times 1/2, which is 0.5. Where was the 1/3? Oh, the 1/3 was after we did all the other shit. So this is gonna keep going. 4 times -0.5. 4 times -0.87. 4 times -1. 4 times -0.87. 4 times -0.5. 4 times 0. 4 times 0.5. 4 times 0.87. And 4 times 1. And then when I do my final calculations, I'll put those values over here in the R column. That way I have R and theta already next to each other. You eventually start thinking ahead and planning for it. 4 times 1 is pretty easy. 4 times 1 is 4. 4 times 0.87 is about 3.46. That's a 2 and that's a 0. And we're gonna have those same numbers repeating, it's just the signs that change. So -2, -3.46. -4. -3.46. -2. 0. 2. 3.46 and 4. We're gonna actually sketch this one cycle. Cause I want you to see what happens and then you'll be able to like identify, hopefully identify the pattern. We got numbers as big as 4. And -4, which is still we're going out 4, but going in the opposite direction. And like I got like values close to like 3.5, so I'm just probably gonna just do 4 triples. I make it kind of big so that it's easy to see the halfway mark, like approximate how far halfway is. I'm trying to do a dotted line where this doesn't make it look like shit when I graph right on top of it. And the bitch is trying to keep these rings equally spaced. And then I'll put my 30-degree tracer lines in. Not a perfect circle, but circular enough. Actually, I don't think this shows enough, to be honest. The way this thing draws out is fucking weird. So my first two columns are the ones that have the radius and theta. So we're gonna plot from that. 4 and 0 degrees is right here. 3.46 and 30 degrees is about halfway between 3 and 4. Wait, but we're at the 10-degree mark. 10-degree mark. 20-degree mark, we're at 2, which is right about here. .30 degrees, which is along that diagonal, we have a radius of 0. So we've got something like this so far. We go 40 degrees, which would be right along about that line, but now we've got a radius of -2. Which means we're pointing, we gotta go out 2 rings the other direction. And it's like, kind of like doing -2 and then 40 off of this one. Which would put us right about there for -2, 40. And then -3.46 is on the 50 degrees. And the 60 degrees is -4. So it's done some shit like this. Actually show the full sketch. Last one I did was 60 degrees. 70 degrees is gonna be -3.46, which is right about there. 80 degrees will be -2. And 90 degrees is 0. We go 100 degrees, we're just past the 90 degrees, we're out 2. 110 degrees, we're out at 3.46. And 120 degrees, we're at 4. I'm gonna add a few more coordinates here that I have pre-calculated here. 130 degrees is 3.46 for 130. I'm gonna go up to 180 so we can see the rest of the graph. It's kind of follows the pattern that we had here, that's a 2. 150. Is effectively. 0, we're tripling it. And then 160 is 420, it's positive. No, negative. $140 is just a little past, 130 is just a little past 120. And we're only out 3.46 or about 3.5, we're there. 140 is at 2. And 150 we're back at 0. And I think you can guess how this is gonna finish out. Everything looks kind of symmetrical right now, other than a certain part. 160 would be going out here, but we're gonna have -2, so we're gonna go out the other direction. Let's see, 160 would be. Just past that line, so -2 there. $3.46 at 170. And then -4 at 180. So we go 180 degrees that way, but then we go -4, takes us over there. These are called the roses. If you have n theta inside. If n is odd, you have an odd number of petals. If n is even, you have 2n petals. Well, your odd number of petals is gonna be the same as your n. We had 3 theta and we had 3 petals. You had 5 theta, you're gonna have 5 petals. You had 7 theta, you're gonna have 7 petals. If n is even, like 4, you're gonna have twice as many, you're gonna have 8 petals. They're all going to be evenly spaced going around the circle. No matter what they are, they're always evenly spaced around the circle. The question is, does the petal start on the x-axis or somewhere else? Again, this isn't gonna be on the test. You're welcome. Other teachers put this shit on the test. That's a fucking major time sink. This takes a while, right? This is a long time for one problem, and you don't even gonna like the answer. Until you get like, if you get the graph looking, this is actually looks pretty goddamn good. This is probably the best rose I've ever drawn. 3-petal rose I've ever drawn. I'm fucking feeling pretty good about that. I'm gonna skim through the next one, show the idea of it, we got like 10 minutes left. It's a more of a pain in the ass of what this does and does follow a pattern. Does anyone need this up longer? So if we had something like r squared equals 9 sine of 2 theta. When we take the square root. You get r equals plus or minus 3 times the square root of sine of 2 theta. So you kind of want to draw 2 curves. R1 is 3 square root of sine 2 theta. And R2 is the -1. And map them both out. You're gonna do the same thing that you did before, it's just more calculations. The last graph we're gonna do, we're just gonna do quickly, we're gonna do increments of. Oh, I don't know. Let's do radians this time. We're gonna do R equals negative theta. So we kind of need to do it in radians because. A degree is not like a distance. So I'm gonna start like negative pi. Negative. What would be closer, negative? Two pi over three. Negative pi over four. Wait. Yeah, negative three pi over four. Negative pi over two. I think I'm making too many here. But that's okay. Then we got pi over three. Pi over four. Oh, I missed one. Pi over six. And then 0. I don't know why I started adding arrows. I kind of want to have like a negative 5 pi over 6 in here. So R is going to be the opposite signs of these. Pi, which is about 3.14. 2 pi over 3 is. Do I have it written down? Should written down. My table over here is wrong. It's two. It's about 2, maybe 2.1. Negative 3. There, negative 3 pi over 4 is that angle. Nine over 4. I don't know. Trying to get this shit in my head. $2.35. I have these in the wrong fucking sequence. I didn't even do the 5 pi over 6. That one's about 2.6. Pi over 2 is about 1.55, 57, some shit like that. Pi over 3 is about 1.05. So negative pi would be over here. And we're going out a distance 3.14. That's my 3.14 and theta. For negative pi. Next one would have been negative 5 pi over 6, which is about 2.6. It's a little bit more inward. You're gonna see this keeps going inward. And when we get down to 0, we're all the way down right there. It makes a spiral that keeps going outward. It's called the spiral of Archimedes if you draw it off. Looks like a seashell, snail shell. Ever growing spiral. Pain in the ass to draw.
Looks like.
So happy that we don't have to draft these on the test. Other tree teachers can make you draft this shit like you need this sometime later in the future. It's more of a being able to recognize, like, there's gonna be weird shape coming on if I see. If I'm graphing something like this, I know there's a weird shape, go look it up. No one's helped about. We got one section left, 8.8 is on parametric equations, that does show up again, and it shows up again a lot. Maybe not calc 1, but calc 2 and 3 are flooded with it. There might even be stuff in calc 1, I don't remember. I don't know, why could they be not, we do, make the spiral or golden rule. You should know how to plot basic points
Yeah.
for a little while.
Yeah, 5 hour.
I don't think so, I know that's not.
Marathon next.